Okay, so hello everyone. Welcome to our this week Rutgers Efficient AI seminar, and also this is our last seminar talk in this semester. And today we're very glad to have the Professor Tim Dettmers from the CMU to give us this talk. And Tim is currently assistant professor at CMU and also a research scientist at the Allen Institute of AI. And his work focuses on making coding agents such as Cloud Code accessible to researchers and practitioners by reducing their resource requirements. And his main research is to develop open source agent systems that are competitive with closed weight agents and can be run on consumer hardware, such as laptops. And his research won oral spotlight and best paper awards at the conference such as iClear and NeurIPS, and was awarded the Block Award, Moderna Prize, and the Google ML and System Junior Faculty Award. And he created the Bits and Bytes open source library for efficient foundation models, which is growing at 4.8 million installation per month, and for which he received the Google Open Source and the PyTorch Foundation Awards. And maybe many of you know that the team has published many very important and pioneering works, especially on the quantization. So we're very looking forward to today's talk about the efficient language model via the quantization. Tim, it's
Yeah,
your
thank you
turn.
so much, Bo. So yeah, this will be mostly a talk about quantization. A big chunk is from my faculty talk when I applied as a faculty. One part will be is updated about sort of modern quantization, what are the limits of quantization. We're kind of reaching where quantization can go, so things are slowing down, and I will talk about that. Um, yeah, it will have a little bit of a background sort of section to sort of get you up to speed, and initial sort of give an overview of the topics that I will talk about will mostly be quantization for inference, quantization for fine-tuning, then also a little bit about how I go about my research that can inform you sort of about the perspectives that I hold. And so basically, I got started with quantization research when I saw these trends. And what you see here is basically beginning of large language models. Language models got larger and larger, but then also better and better. And so now you got pretty powerful models that can actually do many useful things. But the problem was that the models just got too big and people could no longer use them. And so then quantization was a very sort of obvious message of compressing these models to then make them more usable. And so basically, this lecture talks about sort of the process of how I made these models more efficient, what you can do, what the sort of modern practices and so we talk about using these models with quantization, then fine-tuning these models of quantization, and then actually that's not the right topic. It will be state of the art in quantization. And so let's talk briefly about sort of these three sort of sections, and then I give a little bit of background, and then I go deep into each of these sections. And so if we look at using foundation models, that means, for example, using them on laptop, consumer GPUs, or data center GPUs. If you want to make it easier to work with larger models, you got to reduce the size of them. You got to reduce the memory footprint. And that alone is not enough. And you can have methods that are very good at compression, but if you cannot maintain a certain speed of generation or prediction, then it will not be useful. And then also the other factor is if you cannot maintain the quality of the prediction, then it's also not useful. So you need to compress, make it fast, and maintain the quality. And only then something becomes useful. And for that, I developed 8-bit and 4-bit techniques. I was the first that could quantize very large models in 8-bit and 4-bit. And here you see the previously best 8-bit quantization method. And you see a plot here on the x-axis is the model size. And on the y-axis is the mean zero-shot accuracy across several tasks. And so what you see is the performance improves with scale, just like what you expect from large language models, but then it drops sharply at around 6.7 billion parameters, and then quickly it basically goes to random performance. It's just chance, it's just noise. So the model breaks down completely if you use 8-bit. But then I developed a technique called LLM&8, and with that, you can maintain 16-bit precision by basically there is sort of an emergent structure in language models. If you hit a certain size or a certain quality of the language model, then certain structures emerge, outlier features emerge, and these are very, very sensitive. And so if you take these outlier features and treat them in 16-bit, and then you can quantize the rest in 8-bit and everything is like totally fine. Then you recover full 16-bit performance. And these small outliers, they're just 0.1% of the overall weights or corresponding to the weights in the neural network. So I will talk a little bit more about that, how I found these structures and what do they mean. The second major section in this talk will be about fine-tuning, and that goes in the direction of QLoRa. And for that, I want to tell you a little bit about a little story that tells you why this is sort of quite useful. And so I talked with a cancer researcher, and what she was doing is she was taking open source model ESM1. This is a protein folding model, and she was taking database of cancer-related proteins and fine-tuned this model to do her work. That worked really well. AlphaFold is smaller, but generally more powerful. But if you fine-tune the open source model, it's actually more powerful than AlphaFold. And so the cancer researcher, she got really excited when ESM2 was released, much, much larger model, much more powerful, and it's open source, so she can fine-tune it on her database. But what she realized is when she was downloading the source code, downloading the model, she couldn't train it. She couldn't fine-tune it. It was just too big. It needed too much memory. And that has become a really sort of common problem at that time, is the hardware cost to fine-tune the best model was just a couple of $1,000s in March 2021, but then you needed already $700,000 in February 2023. So 1.5 years and you have this big jump and nobody can afford it anymore. And so there comes in QLoRa. It's a technique where you quantize the model to 4-bit, and then you have low rank adapters to fine-tune the model overall. And if you do that in combination, then the memory footprint will be reduced by about a factor of 17. And so that means instead of 3 big servers to train a large model or fine-tune a large model, you can do it on just a single consumer GPU. And that was sort of very powerful. It's quite widely used. The last section I want to talk about is a little bit about the state of the art, and there are basically two state of the arts. Companies, they usually care about a quantization technique that helps them to save money. If they can serve their consumers with a model that is cheaper but still good quality, they would go for that. And what I should also mention there is that is often determined by the batch size. If you have a large batch size during inference, it gets very cheap. And the opposite is true for users. Users just want fast models and they want models that fit in their laptop, but usually they use a batch size of 1 just for themselves. That is very inefficient. So if you use a GPU alone or a laptop alone, you utilize about 5% of the overall computational capacity of that device, but you're much faster. If you use the device alone, you can generate as fast as possible. And that's actually good for consumers. And so you can make it even faster with quantization. And I will talk in that section about the techniques that are currently used to basically give you the best trade-offs for companies or consumers. Before I dive into sort of the background and then the in-depth sessions, a little bit also about how I work, to give you sort of the state of mind for me, how I go about research. And I'll often go through 4 distinct steps. And so the first is really to understand the models, the problem. That means I'm not interested in quantizing this one model, but I want to develop algorithms that are general across all kinds of models. And once you have this understanding, you can develop an algorithm that's truly general and sort of effective. But then the third step kicks in, and that is if you want to design algorithms for particular devices, let's say a laptop or a consumer GPU, you need to change your algorithm to fit with that. You could build efficient algorithms for very big data center GPUs, and that's useful, but it's mostly useful for big companies. It's not very useful for the consumers that often have the most problems. And then the fourth step is open sourcing all of this. For me, it's not enough if I have just a paper on archive or at a conference. I want that people can use my algorithms. And for that, I developed Bits and Bytes, a quantization library that implements all my algorithms. It's widely used across industry and growing now at 6.4 million installations per month. And yeah, it's widely used also outside of computer science. Here, a particular work in particular areas that use it. And with that, we will move to the background. And so the background will be very simple. We talk a little bit basics neural network. You probably all know about this, but I will talk about it anyway, so we're on the same page. And then we actually talk about quantization and how to understand it, how it works. And for that, after that, we dive deeper into the particular topics about quantization. By the way, if you have any questions, you can just speak up, or I'm also looking at the meeting chat, so you can just send a message in the chat, and I'll happy to take any questions that you have. Okay, let's go into the background. The first is resource use in neural networks. And so if you look at this is a transformer architecture. It's very complicated. It has a lot of different moving parts, but there are basically only two layers that are repeated again and again. They consume 95% of all computation and of all memory. That's the feed-forward layer and the multi-head attention layer. Now, if you look a little bit deeper into these layers, what we find is these are just 5 matrix multiplications. That's everything there is sort of computationally. That means matrix multiplication makes up 95% of memory and 95% of computation in a transformer architecture. So if you can make matrix multiplication efficient, you can have very efficient neural networks or transformers. And with that, just a little bit background of what is a neural network. This is super basic. We have an input vector X that represents some kind of information, maybe a word embedding. And so what we do is we multiply by a weight. So if you have 3 inputs, you multiply that and weight each of these 3 inputs and compute a sum, a weighted sum. And if you do this for multiple sort of weights, then you have a matrix, a weight matrix, W1. And if you compute X1 times W1, you get the output X2. And this is called a layer. After that, we often apply a nonlinear function. And if you have multiple layers, what you do is you treat the output of the first layer as the input of the next layer. That means we can pass information to the end of the neural network where we predict a probability distribution. Often what we have is we predict the probability of the next word given all previous words. And with that, we can then sample from this distribution or just take the maximum value to then generate from this neural network. And that's how we use the neural network to generate from it. Now, I said that matrix multiplication is pretty optimal. So we can't improve it with software. We can't improve it with hardware. So the only thing we can do is find approximations that are basically not quite the matrix multiplication that's optimized, but a different version of it that still has the same function. And so there are different ways of how we can do that. The first way is through a low rank projection. So instead of 2 big matrices, 2 big weight matrices, we have a projection that goes down to a smaller one and then is projected up. And so our inputs and outputs, the yellow and blue values still have the same size, but now we reduce the computation a lot. So we are faster, we're more memory efficient, but the problem is this degrades the quality enormously. This doesn't work. You cannot get sort of all of these 3 factors. And as I mentioned before, we need these 3 factors to have something that's useful. If If you don't have one of these, it's not useful in practice. So let's look at something else. This is sparsification. And here the idea is if you look at neural network, the weights are normally distributed. So that means a lot of weights are close to zero. So if you remove these weights, because they don't do anything in the weighted sum, is the quality remains the same. You don't have any performance degradation if you remove these weights that have zero. Now you have weight matrices that are way smaller. And so you think like, hey, I have something really fast, memory efficient, because my weight matrices are smaller. But that's actually not the case. The problem with this sparsification is it's very difficult to develop algorithms that are effective for these sparse patterns. Because of how hardware is designed, sort of modern hardware is designed, is we always need to retrieve elements from the memory that are contiguous so that they're in one sort of place. And if we have sparsity that's non-uniform, then what it means is we don't save any sort of memory access or speed. And because we need to load all the values anyway, because that's how modern hardware works. It cannot selectively load just a single value. You might need to reload like 32 values or 64 values, depending on the hardware. So sparsification doesn't work. Looks very nice on paper, but doesn't work for modern hardware. So what we can do instead is quantization. And so in quantization, instead of having 16-bit weight matrices or 16-bit computation, we do everything in 8-bit. 8-bit weights, 8-bit computation. That's half the size. And turns out this is memory efficient and gives you a good speed up. And if you do it right, you can also get the quality right. So here we have the home run, and we have all three factors that we need to get an efficient and practical solution to improving the speed of matrix multiplication. And with that, we go to what is quantization, how to use it. And so quantization is we want to take a data type that has a higher precision, and now we want to compress it to a data type with lower precision. For example, going from 16 to 4-bit. And if you have a 4-bit integer, its natural range is -7 to 7. And so if you have 16-bit float, the natural range is -65,000 to 65,000. So if we naively convert the 16-bit number, for example, here the yellow dots are a normal distribution, then what we get is we project down. So this means we round the yellow dots to the closest blue dot. We find the closest value in the 4-bit space for each 16-bit number. Then we have this sort of rounding to these values. But now what you see is there are 9 different elements that are not used, and there are no yellow values assigned to them. And so you can have the same quantization that this is with a 3-bit value. So basically you lose an entire bit because you didn't allocate any of these yellow values to the other blue values. How can you improve on that? What you do is you scale the 16-bit number to have the same range as the output number, the output data type. So we rescale the 65,000 to have the range -7,7. And so if we now find the closest value by rounding, what we see is all the buckets, all the blue values are used. And with that, we actually use the full data type. And that gives you much higher precision, much lower error if you quantize. So this is very critical. You need to do this, otherwise quantization doesn't work well. Just to sort of illustrate this, you can view quantization very similar to integer. Integer quantization is very similar to histogram binning. You've probably seen something like this before. For example, you have a sample, which is the normal distribution in red. And now if you want to create a histogram, you need to create bins. And so if you have 16 bins, what you basically do is you take all the values that are in the range of the bin and basically round them to the middle value of the bin. And this is exactly how you do integer quantization. So you create the 16 bins with equal width, You take all the values that are contained and then quantize it to the middle value of the bin. That's integer quantization. And all of this would work very nicely if neural networks would behave well, but they don't. But they often have outliers. And so here, just to illustrate why outliers are so difficult to work with, is I inserted two outliers at the minimum value of 16-bit and the maximum value. Now, if we use the rescaling, what happens is there's still most of the bins go unused. So that means we still have the 3-bit quantization. We have lost a lot of precision that we could have. And to illustrate this with a histogram, this is basically what it looks like. So we have an outlier value at -10, and now all the bins between -10 and -3 go unused. And then we have this sort of normal distribution, but now the white gap between the basically the red curve and the blue bins, you can see that as the error, the accumulated error that this quantization has. And if we quickly go back, what you see here is the aggregated error of these bins is relatively small, but here the error is relatively large because we don't have so many bins to approximate the red curve efficiently. And so this makes the quantization error go high, quantization becomes unstable. So removing outliers or dealing with them is important, or rather, I shouldn't have said that. You can't remove the outliers. The outliers are so important in the neural networks. If you remove them, everything collapses. So that means you need to treat the outliers differently, but you can't remove them in neural networks to make quantization work. And that's one of the main challenges in quantization. With that, we can now dive deeper into the first section, and that is about quantization during inference. Before we do that, we can have maybe a couple of questions if you have any for the background. Otherwise, I move on. You can also use the chat for questions, but it sounds like nobody has questions here, so then I move on. So this is basically what I showed you before. We have model size on the x-axis, mean accuracy on the y-axis, and quantization collapses at 6.7 billion parameters. And so I tried to understand this. And to understand this, I had this experiment. And so what you see here is a neural network with all its weights, and each of the white dots is basically an output. And now the red dots are an output that is an outlier at 6 sigma. So that means it's very, very large, or either very, very large negative or very, very large positive. Now, what I was studying is I take a neural network, then I take a Wikipedia article, I pass it through the neural network, and then I observe the outlier pattern. And then I do this a couple of times, and then I see if there's some kind of structure there. Remember about sparsity. If we have sparse outlier patterns, you cannot develop an algorithm that's efficient. We need to get something more structured. Otherwise, we cannot speed it up and make it memory efficient. And so that's basically what I was looking for. And so in the beginning, I started with a neural network of 350 million parameters. And if you pass different Wikipedia articles through it, you get sort of this pattern. And so while this schema is an approximation, I try to keep these patterns as faithful as possible. And so the patterns that you see here are basically very realistic. That's what you see in a 350 million parameter neural network. Now, if you go a little bit larger, 1.3 billion, then you see sort of these patterns. And then you see there these three values that are already stable, but all the others are jumping around. They're still sparse. But when I saw this pattern, it gave me hope. I saw like, hey, this kind of works. And so I scaled up, which at that time was difficult because the software didn't exist. But we see more structure. And so at this point, I said, okay, probably I need to just scale more. That was very hard with sort of the software at that time, but I got it working. My first experiment with 6.7 billion parameters looked like this. What we have is an outlier at every layer at the same position. And if you change the input, it doesn't change. It's like always the same dimension for every input and for every layer. And so extremely robust structure. And at first I thought like, this must be fluke. Like it can't be such a reliable pattern. So I looked at a different model. And so what I saw is exactly the same pattern. Then I looked at the larger model and used a very different data set, different software, still the same pattern. And so with that, I noticed, okay, probably we have some kind of relationship here. I took all the open source models that existed at the time, put them together, ran them through this benchmark, and this is a plot that I got. Took a very long time to produce this single plot. What I have on the x-axis is language model perplexity. The lower perplexity means the better the language model. And on the y-axis, we have the proportion of outliers. For example, this is 100%. And if I go further back, this might be like 30%. And so if you look at the plot, when I plotted all the data, I got all the experiments and plotted them, you saw this relationship. And so this means as your language model performance basically improves, you see more and more proportions of layers getting outliers. And then at some point you reach 100%. And basically every language model that has a lower complexity than that has outliers in all the layers, and where the outlier dimension is in the same dimension for all layers. And this happens for every input that they get. And so it's an extremely general structure. It is true for language models, computer vision models, and so forth. So extremely reliable. And basically, this is the point where outliers emerge, the structures become stable. And going back to the quantization problem, if you look at the magnitude of these outliers, and we also understand why quantization fails. So if I go back here, so in the beginning we have some outliers, but they're relatively small. And sort of at some point there's this inflection point where outliers become huge. And as I said before, if you have a large outlier, you lose bits in your quantization. And so the larger the outlier is, the more bits you lose. And so suddenly your 8-bit quantization is more like a 6-bit quantization. And so this is basically what makes the quantization unstable. And so now with that, we know the cause and we know the structure. With that, we can develop a very simple algorithm, and that works like this. We do two matrix multiplications, and one of them is in 16-bit for the outliers, and one is in 8-bit for all the other values. Now, because the outliers are so reliable, the structure, we just need one input, pass it through the neural network. We know immediately which dimensions have outliers. These are only 0.1% of all values. We keep them in 16-bit, do a small matrix multiplication with the input, and then we do a very large matrix multiplication in 8-bit. And so with that, we have a neural network that is 99.9% in 8-bit, but we get 16-bit performance. I don't have the 16-bit curve here, but it's basically completely identical. No difference at all. So with that, we know if you understand these structures in these neural networks, if you can isolate it, you maintain the full performance. Neural networks can work with 8-bit and maybe with less bit. And so that's a question I asked myself at that point. Okay, now we know 8-bit, you can just maintain the full performance, but how much further can you compress a model to maintain performance? That's the first questions that I asked myself. But then I thought there's a more interesting question. And this more interesting question is, how can we maximize performance density per bit? Let me show you what I mean with that. So if we have two neural networks, one 10 billion parameters, the other 20 billion parameters, and we quantize one of them in 8-bit and the other in 4-bit, what we have is two neural networks with the exact amount of bits. 80 billion bits. Now, one of these will have better performance, and with that, it has better performance per bit. if we want to maximize the performance that we get in a small memory footprint, for example, we want to run the best neural network that we can have in a laptop, then we need to maximize the performance density per bit. So how well it performs for each bit it has in the neural network. And that's exactly what I studied. And so what I have here is on the x-axis, the total amount of bits in the model. On the y-axis, we have again the average performance on a bunch of data sets. And this is a curve for 16-bit compression or no compression. We know already 8-bit is as good as 16-bit. So the curve is the same, just move to the left because it's more bit efficient. This is a curve for 4-bit, which is still extremely effective. And then this is a curve for 3-bit, things collapse and no longer works. And so this means that 4-bit gives you much better performance density per bit than 8-bit. And what I found is this is very universal. Almost every neural network has exactly this property that 4-bit is optimal. And so beyond that, you can study some other sort of variables in the same light. How can you change the variable so you maximize this performance density per bit? And so I told you about the quantization outliers. There's another way how you can deal with these quantization outliers. And how that works is you slice the matrix into smaller pieces. And now you have the scaling constant that brought the input distribution to the same range as the output distribution or the output data type. And that's exactly what you do, but now you do it for each of these blocks. So if you have a matrix and you cut it in 9 blocks and you have an outlier in 1 block, then the performance degradation, the loss of bits, is confined to this 1 block. All the other blocks will be totally fine. And so you might lose maybe a bit or two in the small block, but the others don't lose any bits. And that's very different if you don't have that, because then you lose a lot of bits across all the blocks or the entire matrix. Now, the problem with this is you need a scaling constant for each of these blocks. And there's a certain block size. How many elements do you rescale? And for example, if you have a floating point for the rescaling and your block size is 32 bits, then 32 elements, that means your floating point is 32-bit. You have 32-bit as 32 elements. That means per element, you add 1 bit of overhead. So if you have a 4-bit quantization with a block size of 32, then suddenly you get a 5-bit quantization in total because you add another bit on top of what you already have. And this is exactly what you can study is what is the best block size? What block size has a good trade-off between basically preventing outliers, but also keeping your memory footprint low. And so what I found there is that you want to have a small block size, usually between 16 and 64. And I studied some other things like that. And if you look at the paper, basically my paper showed that there's a particular configuration that is just optimal. And in the end, NVIDIA implemented exactly that combination of things into their GPUs. Now in the Blackwell, their data types NVFP4, a very effective sort of 4-bit data type that's now supported on the hardware, gives you very fast matrix multiplications. That's basically built exactly on sort of this work of improving the performance per bit that you have in a neural network. And with that, we sort of finish this section. And that is the main takeaway here is if you really understand the neural networks and understand the structures, then you can quantize them more effectively. I'm just looking at the time. We have 25 more minutes. I wanted to leave a little bit for questions. I think it might actually work out with time. Let me just move forward through these sections here. And so the next sort of part in this lecture would be fine-tuning foundation models. And this sort of part is about QLoRa, so 4-bit fine-tuning. I told you already that at some point the cost of fine-tuning the best model was very, very high. And PhD students wanted to naturally work with the best model to do their research, but at this point they couldn't do it. It was just too expensive. And so I thought about, okay, how can we change this? And for that, we have a brief look at fine-tuning, how it works. Before, I showed you that if we pass data through a neural network, we get a prediction. That's how we generate from a neural network. Now, if you want to fine-tune, what we do is we compare this prediction with the ground truth. This gives us an error. And now we use a training algorithm for neural networks, backpropagation of errors. And then we pass the error back through the neural network. This will give us the weight gradients that basically encode the gradient of the error with respect to the weight. If we go down this gradient, we can improve the performance of the weights. So we calculate the gradients, apply the gradients to the weights. Our quality improves on this data set. And that's how we fine tune on a data set. Now, if we want to do it in 4-bit, we do a similar process, but in the beginning, we quantize the model to 4-bit. Then we do 4-bit computation. We have a 4-bit error. We do 4-bit backpropagation. And now we update our 4-bit weights with the 4-bit gradient. And what you see is performance actually goes down. The entire update is too unstable. You can update the weights, but the weights only have 16 different values in 16-bit, and you can only update it in 16 different ways. And that is not stable. You cannot get in a configuration where you can actually train this neural network. And so when I inspected it more closely, I found that the gradients are actually pretty precise, but updating weights is just too coarse. And so I thought about this problem, and then I came up with combining it with low-rank adaptation, LoRa. And this is a technique where you freeze the weight matrices of the model that you want to fine-tune. So you don't change that model at all. What you do instead is you put some small adapter layers. These are just linear projections on top of each layer. And you only learn those weights. And so those weights will influence the inputs and outputs of each layer. And that's how you basically fine tune the model. And so you only update these adapter weights. The other weights, they remain completely the same. Now, if you want to combine these, quantization on LoRa and adaptation, you have QLoRa. And that works like this. We quantize the model in 4-bit. Then we put 16-bit adapters on top. That's important, 16-bit. And now we do our backpropagation. We have a 4-bit error, and we pass this 4-bit error into the 16-bit weights. We get our gradients. We update them, just the adapters. So we update the 16-bit adapters with 4-bit gradients. This is stable. Our quality improves. So with this, we can actually fine-tune while having a 4-bit model. And this works perfectly fine, is as good as 16-bit sort of performance. I will quickly skip this bit. This is basically developing a particular data type that's very effective, that's information theoretically optimal. Yeah, I want to have a little bit of time to talk about the last section. Here, what we see in the results of QLoRa comparing 16-bit, this basically has the same performance. There's no difference there. And this is outdated now, but we also built a chatbot that was actually quite effective, close to GPT 3.5 at that time. And so here the takeaway is that 4-bit fine-tuning is possible if you do the right things in the right position. 4-bit gradients are okay, but we need 16-bit weights, and we can do that with the adapters. The exact same lesson is actually very important today. For example, DeepSeek had the first sort of open source training in 8-bit, and there they did something similar. Certain components have 32-bit, certain components have 8-bit, and if you have just the right combination, you get stable training and high quality results. And with that, I want to talk a little bit about the state of the art of quantization. I will also leave a couple of minutes for questions. But yeah, quantization is slowing down because the solutions get more and more optimal. I already talked about the hardware component. So it's very difficult to beat the hardware in terms of speed. because it's already optimized for the hardware. And if you have some other quantization technique that doesn't run efficiently on a hardware, it will be slower, but it can still be more memory efficient, which has applications. And so overall, there's also the overall picture of sort of theoretical insights into quantization. And there's this paper, Scaling Laws for Precision. And this basically formalized what many people that did research in quantization already knew. And that is, if you train a model on more data, a good view of that is you now push the data into the weights. The more data you push into the weights, the more information they contain. The more information they contain, the more difficult it is to compress them again. So that means if you train a neural network for a long time on a lot of data, it gets more difficult to quantize. And that is exactly what this paper found. So on the x-axis, you have basically, if you train, how many tokens you use per parameter. And so this is a token by parameter ratio. And so if you train on a trillion tokens and you have a billion parameter model, then you are at the very right of this chart. And so what you see is at this point, 3-bit training wouldn't give you any sort of good performance. This is actually post-training quantization, but the graph is almost the same for training, basically. So that means you are just constrained by how much information you can push into the weights. And so even a 3-bit is much faster than 16-bit training, for example. And your overall quality degradation is so large that it's not worth it. And you can't train in 3-bit and get a benefit. And something similar is true for 4-bit. If you use too much data for a too small model, 4-bit training is not possible. And what we're seeing is, for example, the newest DeepSeek model was actually trained in part on 4 bits. And this is particularly done for the mixture of expert layers. And how you can think about this entire problem is each part of the neural network might have a different token to parameter ratio. And for mixture of experts, the token to parameter ratio is actually much smaller. That means it's easier to quantize. That's also what we're seeing in practice. Quantizing a mixture of expert layer to 2-bit, not that difficult. But if you take a dense layer, absolutely catastrophic. It doesn't work. And so this is sort of a good thing to know. These are the sort of relationships. Here we have token to parameter, but in computer vision, models are much easier to quantize, which probably means that the visual concepts that we have don't contain as much information per computational unit as in language, as we have in language. And with that, I go through sort of a couple of papers that make up the state of the art. There has been also a little bit of controversy about ProboQuant, which I also want to talk about. You can think about quantization. So there is the hardware supported method. That's difficult to beat in sort of speed. But what about quality and memory compression? What are the best techniques? And there are basically two camps. One is you don't use any data to do your compression. So you don't look at any calibration set. You don't basically look at what will my data look like that I will process. For example, you could say, hey, I use coding agents a lot, so let's optimize for code. My quantization is optimized for code. Doesn't work well for other data, but it works well for coding data that I have. That's a very reasonable thing to do. And these are basically methods that calibrate, quantization methods that calibrate on some data. The other camp is data-free methods. And it basically says, I don't make any assumptions. If I make some assumptions, my model might become unstable. For example, you have a coding agent that's optimized for code quantization. But what about your coding agent suddenly reads documentation and it's really, really bad documentation? Even worse, it might be pushed in a sort of certain space in the model weights where the quantization is so bad that it produces gibberish and it can never recover from that. Once it's in sort of a certain loop that's very sort of poorly defined in the generation space, it will not recover. And so the data-free basically perspective is let's not use any calibration data so that we have guarantees that the degradation is uniform. Every data set will have similar quantization degradation, and we don't favor or disfavor any sort of data type or any data set. That's the data-free sort of perspective. And so this particular paper shows that theoretically and also empirically, it's basically the best you can do in quantization if you don't use any data. If you don't make any assumptions, this is basically the best you can do. And for that, this paper uses two different techniques. One is vector quantization. The other is Hadamard rotations. And so I will go briefly through these concepts. And so the first is vector quantization. And so usually what we have is in quantization, we have, for example, a 16-bit number. We want to quantize it to 4-bit. Now with vector quantization, what we have is we have multiple numbers, and now we quantize it to one value. So how do we do that? For that, we need a codebook. And this codebook's in the middle here on this slide. That codebook, for example, encodes the value 0.1 and 0.2 or 0, 1.0. And what we do with the inputs is we take multiple inputs at the same time. And now we look for the average distance across multiple values. For example, if we have the input, the first input, 0.1 and 0.3, then this is very close to 0.1 and 0.2. And so that means the first two values get quantized to the value 0. So we transform the 0.1, 0.3 in just a single number, 0. And we do this for all the values in the inputs. We look up in the codebook that has multiple dimensions. We calculate the distance and then round to the closest, basically, entry. That gives us a single number in the final quantization. And if you want to reverse it, you just do it the other way around. You take your index, look up the codebook, what values it represents, and then you get basically back your full matrix. Now it's of course quantized, so the first value, the 0, if we do the lookup, it becomes 0.1, 0.2, and then basically we get back in the top left corner, instead of 0.1, 0.3, we would get 0.1 and 0.2. That's the quantization error that we have. So this is vector quantization, and it's very effective, and it sort of has better performance. And I give you a little bit of intuition why that is. For example, if you have a normal distribution, then at the end you have very large values, very large in magnitude. And the thing is, if you have basically a data type where you quantize some values to these large values, then you have the problem that very few of these values are large. That means certain bins that you have, so you, for example, 4-bit, you have 16 different values, 16 different bins. And now you need to sort the inputs into those bins. If you do sort of a linear mapping, then the bins at the edge will not have many values. Basically, your histogram mirrors the overall sort of distribution. Now, if you want to basically have a quantization where each bin has equal amount of values, what you want to do is something similar to vector quantization. You basically want to combine the large values with the small values, for example, and that gives you a value that one value might be very rare because it's large. Another value might be very common because it's small. If you combine them, they have about equal chance than any other value in the codebook. And that means each of the 16-bit values, for 4-bit values, so 16 different combination, have about equal probability to be chosen if you have a normal distribution. And that is why vector quantization gives you better quantization performance than as if you only take a single value. because you can account for the overall distribution of values. And the second sort of concept is Hadamard rotations. I talked quite a bit about outliers and how to prevent them. Hadamard rotations is probably the most effective way of removing outliers. And so how it works is this is an operator where you basically transform an input in such a way that all the dimensions are shuffled up so that the outputs are a normal distribution. This is also used in the wave function and quantum mechanics. Basically, you want to get basically a distribution, a probability distribution that's normally distributed. And so you want to take any input and transform it so it gets a normal distribution. And this is exactly what Hadamard rotation does. But the Hadamard rotation has a second property, and that is if you multiply two values that are transformed in the same way, then you recover basically the same value through a matrix multiplication. So this is the identity. If we take X and W, then we get that matrix multiplication basically. But now if we rotate by the rotation matrix Q and then multiply, so these are normally distributed matrices now that are sort of shuffled, and then you still recover the normal matrix multiplication. And so the rotation part matters because if you have large outliers, they're shuffled around, their magnitude is sort of spread across many dimensions, and suddenly you don't have any outliers anymore. They disappear. And so now it becomes really stable. And the other thing is it becomes a normal distribution. So if you have a code book that is optimized for a normal distribution, and you have an operator that gives you a normal distribution, you get extremely good quantization performance. And this is exactly what this paper does. It develops the Higgs method, and that uses basically Hadamard rotation and a code book that's optimized for normal distributions. That's called Lloyd Max optimized code book for normal distributions. And you can show in theory this is optimal for language models if you don't make any other assumptions. And empirically, this is also true up to 3-bit. At 3-bit, something weird happens, and the theory diverges from sort of the empirical data. And this is basically the plot. So the blue dots are the empirical values, and the dotted line is the theoretical value. And so, yeah, it diverges, but it's almost basically perfect until 3 bits. So we know this is basically the most optimal method that you can have at 3 bits if you don't use calibration data. These are the results. We don't have to go into that. Basically, it's the best method that you can develop. We have a couple more minutes. I'd rather take questions than talk about more details. There's sort of a couple of other things we could talk about, but I think it's better to take a couple of questions. We have 5 more minutes. You can leave the questions in the chat or just ask me directly.
Hello, Tim. Fantastic talk. Thank you for your speech. And I have 2 questions. The first one is technical. Could you go back to the page 95? It's about a precision
Yes.
problem. Yeah. Oh, I think no. Sorry, it's not 95. It's about you have your formula, 2 number plus one is 8-bit, one is another is 16-bit. Do you remember that page?
So say again.
You propose a formula. There's 2 parts. One part is
Oh
8-bit,
yeah,
another part is 16-bit.
that's this year.
Yeah. So the
Yeah.
question is like when you have 2 number in different precision and you
Mhm.
plus them together,
Yeah.
what is the precision of the result? It's still like 16-bit.
Yeah. So basically, if you convert an 8-bit number into 16-bit, you can always recover the full information. But if you go from 16 to 8, you can't. And so
Okay.
usually neural networks, the matrix multiplication is one precision, but after that you have other operations that often require different precisions. For example, Most layer norms or RNS norms just take 16-bit inputs. Most other functions are required to have 16-bit inputs. So you would actually want to convert it to 16-bit. So what you do is you take the 16-bit outputs, the 8-bit outputs, convert the 8-bit into 16-bit, then put them together. That's your final output.
Oh, got you. So the whole neural network, the final result is 16-bit because the intermediate, some neurons are 16-bit. Okay,
That's right.
got you.
That's right. Yeah, it's just for the matrix multiplication. You just do the computation in 8-bit. You can keep the weights in 8-bit, but the outputs will be converted to 16-bit.
Okay, so you will there give some burden because the type conversion, the 8-bit to 6-bit, will there take some time for the efficiency?
Yes. So this is, if you implement it well, it gives you a little bit of speed up, but it's very difficult because that conversion will give you overhead. The real
Okay.
reason why it's actually slow on modern hardware is that the transpose operation is not supported. So on the backward pass, it's much more complicated to do this, but the quantization is part of the overhead. So yeah, that's basically a price that you pay.
Okay, got you. Thank you. Another question is about the page 27. It's about meta research. So at first you talk about, I think the pipeline, how you do the research, right?
Yeah.
Yeah. So, oh yes, I understand the models and all these things. I think when you deliver this presentation, when you talk about your papers, you always propose some questions. Some questions very interesting, and you propose you find some patterns solving. So I want to know like when you are doing research, what is the success rate when you to solve the question you found? How many questions, like you find 100 questions and finally you find only 10 questions are solvable. So how do you feel about that?
So yeah, there are many different sort of approaches to how you do research, right? And I've
Yeah.
seen extremely successful sort of researchers that do more incremental work in the sense of they look for important gaps in the literature and then fill them. What I often did in sort of research, I did very risky projects that sort of tried to go sort of beyond. And often, if you want to do these projects, you have to first really understand it to make the big leap. If you want to
Yeah.
make bigger leaps, you need that understanding. But these projects are also risky. And so in the first 4 years of my PhD, I didn't publish at all because all the projects that I did failed, basically. But in each project, I tried to get this understanding, and this understanding actually helped me to then develop sort of these methods. So it's a different process, a difficult process, and different people have sort of different ways of approaching it. But yeah, that's sort of my style.
Oh, thank you. So you spent 4 years to explore.
That's
Oh,
right, yeah. And
okay.
it was always about efficiency, but I spent a lot of time on mixture of experts. I couldn't get anything working, lots of different architectures. Developing new architectures is very difficult if you want to
Yeah.
really have them work and scale. Very difficult. I tried it for a long time, didn't work. I tried a couple of other things, but then quantization is really where it, sort of everything worked out.
Oh, that's really awesome. I respect that very much. So you have this curiosity to do your research and you take your time. Okay. Thank you for your answers. It's very good. Thank you.
Some other questions from the audience?
Hi, Dr. Dettmers. I have a quick question regarding the like the quantization data type. So in your slides, we know that like we often use the integer numbers to represent the quantized values.
That's right.
But intuitively, why won't we use the like floating point? Because intuitively, the data distribution might be more similar between the floating point numbers. Is there any reason we do that?
That's right. So in this paper where I looked at the basically performance density per bit, I actually also looked at data types. And there I clearly found that floating point is better than integer. If you talk to hardware people, they would say integer logic is smaller on the chip. So you can put more integer logic on the same area, which sort of counterbalances a little bit. But in the end, floating point is still most effective. The other thing I looked at is basically if you have information theoretically optimal data types, that's even better. but that's very difficult to implement in hardware. So one basically data type is good for compression. The other bit is to run fast on hardware. There, the best answer is on hardware, you want to use a floating point. And if for compression, you want to use something that's closer to information theoretically optimal. That's sort of the results. Integer is actually never good, really. Like, yeah.
Okay, I see. It's like a mostly efficiency issue on the hardware. Got
That's
it.
yeah, and also performance. The performance
Oh,
density per bit cannot counteract sort of the efficiency on the hardware side. So floating point always gives you a better trade-off in terms of runtime speed and quality.
got it. Got it. Thank you for the answer.
I want to maybe quickly answer one question in the chat. And so and then that is in VLLM. Quantization is often applied to the weights, but computation is still done in sort of other and higher bit precision data type. So the most widely used sort of paradigm, particularly for inference, is this. So every frontier lab will have inference in NVFP4. And that's the standard now. You combine it with Hadamard rotation in this. But this is not true for certain computation. For example, for flash attention, it's almost impossible to write a 4-bit kernel that's faster than a 16-bit kernel because there the softmax is very important, expensive, and the scales that you have for normalization are too expensive to combine. So for that, you convert to 16-bit. Similarly, for mixture of experts, they're so bandwidth bound in the decode step that you want to actually use the most memory efficient quantization, not the quantization that's supported by hardware. So these two are exceptions. Otherwise, you always want to use this NVFP4 data type now supported by Blackwell. Okay, I think we're out of time. Happy to take one more question, but I think, yeah, we're out of time.
Is there any further questions from the audience? Okay, so if no more questions, let's thank our speaker again, team. Thank you so much for give this very informative, very wonderful talk, and we really learn a lot. Especially we know right now, so the area, as mentioned, area of the generative AI, so the efficiency, the quantization plays a very central role. Yeah, just in my last week's deep learning lectures, so in the class, so I think quantization right now is kind of the dominated compression method as compared to other previous pruning or low rank. So, and I believe that right now is also there's still a lot of the space and headroom that we can further explore. Considering right now this like the KV cache, all the stuff becomes so resource consuming and so on. Yeah, and also thank you so much give us the talk, and also look forward to your future wonderful work. And
Yeah,
also,
thank you so much.
yeah, go ahead.
Yeah, no, this was really fun. Yeah, thank you for inviting me here.
Okay, thank you so much, and also thank everyone to attend our this week's talk, and this is our last talk in this semester, and we will continue our Efficient seminar talk in the fourth semester. So thank everyone, and hope everyone enjoy a wonderful summer. Thank you, team. Thank you.
Thank you.
Thank
Thank you,
everyone.
Okay.
team.
Bye.
Thank
Bye.
you. Bye bye.